minus 0.1 is 2.1, 0.9 is 2.1, okay? And if you have a difference that is larger than 2 of the electronegativities, then you have ionic bonding. There's a complete charge separation. That chlorine pulled that electron off that sodium, and the chlorine is negative and the sodium is positive. That's the sodium is the cation and the chlorine is the anion, okay? So then you have ionic bonding. That's essentially the strongest bonding you could get. And then you have the other case where you have, it is about between 0.4 and 2. So then you don't have ionic bonding. You have essentially covalent bonding. I can call it partly ionic, or I can call it polarized covalent. It's the same thing. So this morning I had this sort of idea. It's like when two people, like partners, a married couple, let's put it that way. They lay in bed, okay? And the one guy pulls the blanket, or one partner pulls the blanket away from the other one. And that's what actually they do with the electrons. The chlorine is the one who pulls, that's the bad person, pulls the blanket away from the hydrogen, so it has more blanket, so it's more negative, and the hydrogen is sort of lays there without the blanket, okay? And so it's not so positive, but in this case it would be positive. It's polarized covalent, okay? So you can see the blanket is the electronic cloud, and it pulls it more over because it's more electronegative, all right? So I don't know how I got to this morning, but nevertheless. And so this is polarized covalent, and then you have covalent bond when the difference is smaller than 0.4. That means you have to have two atoms which are very close, essentially the same electronegativity. Then you have if you have two of the same atoms binding to each other, then you have a perfectly covalent bond, and delta would be 0 actually, okay? So there's no polarization in there. So this was this here, okay? So I talked about this here, covalent, polar covalent, ionic. I just explained that. And so this is the ionic bonding. We did this here already. So it pulls the electron over. The lithium and fluorine is very electronegative. This becomes positive because it gets an octet here. The sodium gets positive. The chlorine becomes an octet. So this is the first group with the second to last group. And then you have, this would be what? Covalent, perfectly covalent bonding. Hydrogen, duet, chlorine has 7, Lewis structure, 2,4,6,8 here. And HCl, of course, there you have the blanket puller, okay? That's the chlorine pulled the electron over here. So this would have a dipole moment, wouldn't it? And the dipole moment goes from the less electronegative to the more electronegative, right? Dipole moment is this here, less electronegative. This guy has the blanket partially, and this one has partially not the blanket. And so it goes from plus to minus. This is the vector for it here. It always goes in the direction of the more negative, and the length tells you how large that dipole moment is, okay? So then we have exceptions to the Lewis octet rule. So we try to follow the octet rule. We have discussed all this. This is you probably know by heart. And then there are exceptions. For example, here, this would be xenon tetrafluoride. So what would be the electron geometry for this? The electron geometry. What's the steric number of that? So what is it? Octahedral, okay? All right. Just think before you do anything, okay? That's because you will shoot yourself in the wherever. Okay, you can hear me? You're still somewhat with me? That's good. And then you have not enough electrons. Boron trifluoride. What's the steric geometry here? The molecular geometry and the electron geometry. Trigonal planar. If you want to make a hybrid orbital, what would we use? sp2, exactly. And here, what would we use here? sp3d2. Excellent. You guys are good. You must have a good teacher. Okay? I want to meet him one day. Okay? So then we talked about formal charges, how you determine formal charge when you have these tricky Lewis structures. You have to, especially when you have resonances, you need to decide the least formal. There's some rules, and we go through these rules now. Formal charge is the number of valence electrons on the free atom, and this applies to Lewis structures, okay? The number of valence electrons on the free atom, and you compare this with the valence electron on the unbound, in the bound molecule of that atom, okay? The free atom minus the unbound, and the difference is the formal charge. And you need this in order to do Lewis structures. So you assign the lone pair entirely to the atom where it came from, okay? You don't share that. You share the electrons, and they are divided equally between the sharing atoms. Divided equally, okay? Now, then the atoms and molecules try to have formal charges as close to 0 as possible. So if you have too many formal charges, there's something wrong. And the negative formal charge, of course, has to be with the most electronegative atom. So if you give the electropositive the negative formal charge, you're also doing something wrong, okay? And we then talked about the valence shell electron pair repulsion model. The VSBR model can be used to predict molecular shapes and geometries. So we had a steric number that determined the geometry. The lone electron pairs are positioned to minimize electron repulsion, okay? Now we had a couple of examples there. So we go the steps for draw the Lewis structure for the molecule, use any of the resonance structures to predict the molecular structure. Count each, that's why you can do that. Count each multiple bond as a single effective pair, all right? Count the electron groups around the central atom, determine the electronic shape, the electron shape, arrange the electron groups to minimize repulsion, and with this you determine the molecular shape. So there's the electron geometry and molecular geometry. So now we can go through that here, okay? Linear is steric number 2, steric number 3, you know all this, don't you? Steric number 3, no, not everybody knows that. Steric number 3 is trigonal planar, 120. Steric number 4 is tetrahedral, 109.5. But now you can have lone electron pairs, okay? So this one here, this would be the electron geometry here, trigonal planar, but this would be angular bend here if you have here a lone pair, okay? Now you have tetrahedral, that would be ammonia, NH3. So what do you call this thing? Let's see. What do you call this thing here? NH3. Where's the lone pair? It's up here, okay? My battery's dying. Here's the lone pair. And so what is this? Is NH3, isn't it right? And what would that be? Water, H2O. How many lone pairs do we have? Oh, it says right here. 2 lone pairs, okay? So what's the angle of this compared to that and the angle of this compared to that? Less. Why is that less? Electron pair repulsion, okay? They're pressing on the angle. And what's the angle for water? 104.5, yeah, okay? And the angle on ammonia? 107. Good, because why? You have only one lone pair. All right? I'll get it together here. That's called pit stop. Okay? I don't know if they're much better here, but anyhow. So the trigonal bipyramidal has 1, 2, 3 in the plane, okay, in the trigonal plane, and 2 form the pyramid, 1 here and 1 here. And so you can have, if you have a lone pair, you could have this here, that's like a seesaw, okay? Or you have 2 lone pairs. Where would you put these 2 lone pairs here? They go here and here. That would be a T-shape, okay? That's in your book. And octahedral would be square pyramidal. That means you have the lone electron pair here. And square planar would be a planar thing, but you have 1 lone pair here and 1 lone pair there, okay? So then we talked about isomers. Isomers are molecules of the same formula with different arrangement of atoms. You have structural isomers. versus stereoisomers. So let's see. This has the same number of carbon, hydrogen, and oxygen than this. It's a totally different compound, totally different structure. The carbons are bound together. Here's an oxygen in between. Totally different, same molecular mass, totally different compound. These are structural isomers. This is a delicious molecule, and this is ether here, okay? And for some people delicious, okay? For some people not so good. And now then you have stereoisomer. There the differences are very subtle. The bonding partners are bound to the same carbon, for example, here and here, Cl and H, Cl and H, and here Cl and H and Cl and H. But nevertheless, there's an isomerism. This is trans configuration. So this would be not polar, wouldn't it be? Because that would be one momentum here and the other momentum in this direction. So this is non-polar. Now this is the cis configuration on the same side. That would be one momentum goes from where to where, from here to here, and one from here to here. So that would be the component, the vector addition. That would be would have a magnetic momentum. Yeah. Okay, chirality. These are stereoisomers. They have no superimposable image. So an isomeric center is always one molecule that has four different things around it. And so this is only can be congruent with its mirror image, just like our hands and feet. We are actually chiral. Now, as I said, chiral molecules have chiral centers. Okay, and generally have chiral centers here. And you see here there would be a chiral center here. Where would be the chiral center? In the middle. This has this around there. This has one. This has this, and this has this. That would be a chiral center. This would be alanine, an amino acid, and this would be the D. Has also a chiral center. That's the mirror image of it. And I remember there was one question in the midterm where you have a D and D together, not in the midterm, in the chem quiz. You have a D and D, you bind this together. So each of them has still a chiral center, and because it's D and D, the new molecule is also only a mirror. It can have a mirror image as its isomer. Okay, and L and L would be the same. It's still each of them has a chiral center. So that's a little tricky question. That's why I usually omit that question. But you have an L and a D together, and they are bound together. They still have a chiral center here and a chiral center here. But the molecule itself doesn't necessarily have to be chiral because this is not. You can image this without a mirror. Okay. So when I ask you about chirality, I always ask about a chiral center. I'm not going to make it so complex. All right. So not DD and LL and DL. All right. That's the next level. You do this the next time. Good. Then we have bonding. So let's see. Bonding, we have an anti-bonding molecular orbitals. That means these atomic orbitals, they combine to a bonding molecular orbital and an anti-bonding molecular. We have one here. They combine when they bond to a bonding and to an anti-bonding. Because you start out with two orbitals, you have to come back with two orbitals. Okay? So the anti-molecular orbitals are filled with electrons similar to the atomic orbitals. Stability of the molecular orbitals depends on the bond order. And we had this here. The bond order was the number of bonding electrons minus the number of anti-bonding electrons divided by 2. Isn't that right? So in this case, the helium would have bond order 0. And this would be a sigma bonding and a sigma anti-bonding. Which one has the higher energy? This one here, the sigma anti-bonding, okay? And if you have bond order 0, there's no bond, no game. And so this would be, helium would be closed, that would be the closed core orbitals, okay? You can't forget about those. But then you come to the next period, you have lithium. So you have, each lithium has one, 2s1 each is the configuration. Now you have, from a bonding, you have this anyway, okay? You have, because this is the one below, this you cannot forget about this, but it doesn't bond anything, because the bond order is 0. So you have one from here, from the one lithium, and there's the other lithium, imaginary lithiums I have here, okay? You put them down here, and one here. So bond order of this would be 2 minus 0 is 2 divided by 2 is 1. Yeah, okay. And beryllium is the same bond order 0. Okay. Now bond order is number of bonding electrons minus number of antibonding electrons divided by 2. Now if you have p orbitals, they can overlap in two different ways. They can, if they are side to side in the interatomic axis, okay, then they overlap here or overlap here, and they form a sigma bond. Okay. But you have also the possibility because you have 3 p orbitals, 2 of them form pi bonds. Each of them, if you have two bonding with each other. One is this one, that's head on head, toe on toe. So head and head forms one red, for example, and the blue would be underneath. The bonding, the sigma bond would go right on here, okay? And so then you have another one, the x direction, that's the one through the front, head to head, toe to toe, okay? And so you have the sigma bonding and the sigma anti-bonding. This is the bonding one, is lower here. That's in phase, that's out of phase. And this one is the p set, and the px comes out of the plane, okay? That's not written here. So you get the bonding looks like this, and the anti-bonding looks like this. Now here it is again. So you have the sigma bonding and the pi anti-bonding. So you have 2 pi's you can build from 3 orbitals. And that means if you have valence bond theory is another cop-out here where we hybridize these atoms right there before we do anything. We get them in the right shape. We combine the wave functions of the unbound atoms at the atom to get them ready for bonding. Okay. Now the tricky one is, for example, carbon. You have a 1s2, you have 2 in the s, and then you have 1p, 2p. Okay. But there's 1p because you have 3 p orbitals, because even if it's not used, you can use it. So what you would, for example, do with a let's see, if you have carbon with a double bond. Okay. So how do you get the carbon with a double bond? Usually you have a single bond. And let's see, you have an sp2 hybridization, okay? sp2, there would be a hydrogen here, there would be the carbon, and it form a sigma bond with the other one, if you have CH2, CH2, okay? So how do you get the double bond? You use one s, and 2 p's you use. But then you have one left in the s, and this is where you hang up at times. You have one left in the s, that can go into the p. It doesn't care, because you already manipulated these orbitals anyway. So you have one p, you put this one electron in the p orbital, and with this now we have 2 p orbitals side by side, and they overlap, they form the sigma bond. And this is the second bond. You can't have 2 sigma. Did I say sigma bond? That's wrong. They form the pi bond, okay? They form the pi bond, okay? It's head to head, toe to toe. You can have only one sigma bond and 2 pi bonds, okay? The VSBR geometry is used to determine the hybridization. So we talked about this earlier already, and you were pretty good at this. You even D2, SP3. And so you have the SP2 is linear, and you have the SP2, SP is linear, the SP2 is, what is that? Trigonal, this is tetrahedral, and then we come, now we come to the example I just showed you. This is what I wanted to tell you. You have 4 electrons, okay? You form 3 SP2 orbitals, okay? SP2 orbitals, and this overlaps here. There's the other ones. This and SP2 will bind, each has one electron in there. Will bind to the hydrogen here, and this overlaps here from the sigma bond. But now you have the p orbital here and the p orbital here, okay? They overlap to form that pi bond. And this would be, the pi bond would be in this case the py, as we define this as y. Py overlap gives you that pi bond here. Did you get that? Okay, you're hybridizing. So he said, he said, I'm using an S, and I only have 2 p's here. So I get stuck with an S there. No, that you can use the third p, put that electron in the third p, count the number of electrons, exactly, and then start hybridizing. So, and then we have here the d orbitals, SD, sp3, that gives you that shape, and d2, sp3, d2, and d2, sp3 gives you the octahedral shape. Now, I have a question for you. Of course, it comes at the end. We have plenty of time. Formaldehyde is planar. which best describes the p electron density. So there's a carbon and oxygen here. There's a double bond here. So what would be the hybridization on this one here? It is planar. You see that? And what would be then the second bond? How would it look like? Would it look like this one, or like this one, or like this one? Okay, you have 35 seconds left. You're doing well in time. That was the answer I got this morning too, okay? C is of course right. And so let me explain this to you. So what's the carbon? I said it's planar. It has 1, 2, 3 partners. What kind of a hybridization is it? sp2, that's what I just explained to you. sp2, okay? And so what is the oxygen? It's also planar, sp2. You have an empty one here and an empty one here, and this is the sp, okay? So now this is planar here. There's our plane. And now what do you have here? You have here p orbital, here p orbital, and here p orbital. Is that right? Okay? So they overlap. How would they overlap? Like this, or like this, or like this? They overlap like this. And if I would have the other direction, that would be the py. If I have the px direction, you only see that lobe in the front here, okay? You can't see the one in the back. So let me ask you the final question. Was this review helpful? You have another minute. And with this, I see you either in office hour or on Monday, and what I talk about on Monday will not be part of the midterm. Have a nice weekend.